Polynomial functions. Let's start with the definition of a polynomial. A polynomial is a term or a finite sum of terms. So let's stop there for a second. A term may be something like x squared or 3x to the fifth or negative 2x cubed. Okay, these would be terms. So it can be one single term, or we can add a bunch of terms together to form a polynomial. The word finite here just means that at some point we have to stop adding. So something that would not be a polynomial would be some sort of pattern that goes on forever, like something like 1 plus x squared plus x cubed plus x to the fourth dot dot dot. The dot 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 would not be finite, so that would not count as a polynomial. Okay, so a term or a finite sum of terms with only 0 or positive integer exponents on the variables. So let's test this out. Is it a polynomial? Here's 4 options. Let's look at them one by one. So option A, is this a polynomial? I think yes. We have 4 terms here that are either added or subtracted together. So yes, this is a polynomial. What about B? We need to have integer exponents. An integer would be a whole number, a positive or negative whole number. So this would be a no, and the reason is because we cannot have an exponent of 1/2. This is a no. Okay, and an exponent of 1/2 is the same as a square root. So if I'm not allowed to have a fraction exponent, that means I can also not have any square roots or cube roots or any kind of root to be a polynomial. Okay, what about C? I want either 0 or positive integer exponents. This one is not positive, right? So that would be a no. And 6x to the negative 1 power is the same as 6 over x. That negative exponent is that reciprocal, so it sends it down and across the fraction bar into the denominator this time. So any fractions that have variables in the denominator would also not be polynomials. Okay, what about D? The answer is yes. The number itself, 6, is a polynomial. We said it could be a single term. This would be one term. If you're bothered by the fact that there's no variable there, you could think of it as 6x to the 0 power if you want. Anything to the 0 power is 1, so that would be the same as 6. But yes, this would be a polynomial. Okay, so that's the definition. So you have an idea of what we're working with. Most of the things that we're going to be working with have one variable, like the choice in part A here. And we're going to write it in descending order from highest power of x down to lowest. So that's sort of what we'll be working with in this chapter. There's also some vocabulary that would be good to review before you head into this chapter. So the first one would be the degree of a polynomial. The degree gives the highest power on x, or I say x, but whatever variable we're dealing with. So in part A up there, we had 5x to the third minus 8x squared plus 7x minus 4. The degree would be the highest power on x. That's this 3. So for this polynomial, the degree would be 3. Okay, so that's degree. We're going to be using or discussing the degree of polynomials a good bit in this chapter, so it's good to make sure you understand what that is. Then we have a 0 of a function. A 0 is an x value that makes the function equal to 0. So if we set f of x or y equal to 0, that will allow us to solve for the values of x, okay? And a 0 can actually be a real number or a complex number because it is just a value, an x value that makes it 0. So it could be both. In our class, we're just going to be looking at the real zeros. And so anything that's real will also show up on the graph. And so the zeros that we're dealing with will show up as the x-intercepts of the graph. And it'll be the points where we have a number for x and we have 0 for y. Okay, and then the last thing is a turning point. So a turning point, I think you can probably guess, is where the graph makes a turn. Okay, in order to count as a turn, it has to change from either increasing to decreasing, which would be a turning point right sort of at the top of this hill, or it could be from it's going decreasing and it makes a change to increasing, and that would be a turning point as well. If we don't change from increasing to decreasing or vice versa, even if we do a little squiggle, but we're either continuously increasing or continuously decreasing, it doesn't count as a turning point. It may be an important point for that function, but it's not a turning point. Okay, so now we can sort of put these two things together a little bit and talk specifically about the graph of a polynomial function. This is just some general information that's good to know about this type of graph, and then we're going to take some time to analyze the specific parts of these graphs as well. So the graph of a polynomial function with degree n, so that means the highest power on x is n. And then I'm going to be general here, but if you want to think about the degree being, let's say, 5. Okay, so x to the 5th is the highest power on x. You could think about that if you wanted a concrete example. Number 1, the graph for the polynomials is continuous. Continuous is a math term that has a specific meaning. The informal definition means basically that the curve is connected, so that if I were to draw the curve on a piece of paper, I would not need to lift my pencil from the page. I could just continue drawing. There would be no breaks, no jumps in this graph. And the graph of a polynomial has smooth rounded turns. So no sharp corners, no like the absolute value has that V shape with a sharp corner, none of that, just smooth rolling hills and valleys. So if we put these two together, pretty much the graph of a polynomial is going to look like a squiggle. That's what I like to call it. Okay, so we're going to be talking about what the shape of this squiggle looks like based on what the polynomial is. Okay, and then we can talk more specifically about the zeros and the turning points. So if the highest power on x, if the degree is n, then the graph can have at most n real zeros. So if you want to put a hard number in there, if x to the 5th is the highest power on x, that means we can have at most 5 real zeros. It could be 5 or it could be less than that. And we're not including the complex zeros here in our discussion, but those are part of it. So in our case, that means that we may have less than the degree if those complex zeros are there. Okay, and then the graph can have at most one less, so n minus 1 turning points. So if you put your x to the 5th in there, that means for x to the 5th, we could have at most 4 turning points. It might be 4 or it might be less. Right? Okay, and if you put those last two together, if you think about what the zeros mean, right? These would be the zeros where I'm touching the x-axis. In order to touch the x-axis twice, I would have to somewhere in between make a turn to come back. So between each pair of zeros, there must be at least one turning point. Maybe more, but there's at least one. Just based on the idea that this is a connected curve and it has to return to the x-axis. Okay, so the main part of our discussion for this section is going to be centered around these 4 topics for this type of function. We're going to talk about how to find the zeros. We're going to look at what's called the end behavior, what happens at the ends of this graph. We're going to talk about what's called the multiplicity. This affects how the graph, remember it's a squiggle, so how does it interact with the x-axis? Does it touch or does it cross over? And then the last thing is we're going to talk about how to find the turning points. We're going to use our calculator to do that. So we're actually going to talk about the first 2 of these in this video. This is part 1 of video, I think it's 27. Okay. And then in the part 2, we're going to talk about the second pair of these 2 things. Okay, so let's take a look. So if we want to find the zeros of a polynomial, this is really not a new skill. This is something we've done before. For us, the zeros are just the x-intercepts. So we're going to solve for them in the same way we would to find the x-intercepts. We're going to make the y, or the f of x, 0. And then we're going to solve for x. And we've looked at lots of tools at this point that we can use to help us solve. Okay, so I've written this as a function just because that's kind of what we're talking about, and that's the context we're going to talk about these ideas in. But the f of x, remember, is interchangeable with the y. So if you would prefer to see a y, you can always put a y in there. We're going to make the y equal to 0. And we're going to solve for x. So how can I solve for x here? I can add the 162. And then I can divide by 2. To remove the exponent of 4, opposite of an exponent would be a root. Come over here. So I can take the 4th root of both sides. Now for a 4th root, which is an even root, I need to include that plus or minus. I don't have to do that for an odd root, like a cube root. I don't have to worry about that, but for a square root or any even number, any root with an even index is what it's called, I need to put the plus or minus. So on this side, these cancel out and I just get x. Do you know what the 4th root of 81 is? You can do it in your calculator. 81 is 9 times 9, and each of those 9s is 3 times 3. So that's actually 4 3s. So I have plus or minus 3. Or if you wanted to list them out separately, 3 and negative 3. Okay, these would be the zeros. If you want to write them as x-intercepts, okay, and this is sort of a semantics maybe, but usually when we talk about them as x-intercepts, we list them out as a point. Remember, we started out by making the y value 0, so these are the x values. So we had one point at 3, 0, and another point at -3, 0. These would be the x-intercepts. Okay? And so if we were making the graph of this function, we would take and plot these 2 points right on the x-axis. Now, notice the degree here is 4. I'm going to write that up here. Okay, so we could have had up to 4 zeros or 4 x-intercepts. We only found 2. So remember, it can be 4 or less. And this time we have 2. For this function, and you can't really see it here because of the way we solved, but for this function, there are actually 2 real zeros and 2 complex number zeros that would total up to 4. Remember I said we're only going to be responsible at this point for finding the real ones. Okay, let's look at a second example. We could do the same thing here. The f of x is like our y, so we're going to make y 0. And then we want to solve for x. What solving strategy is going to work the best here? I have 4 terms, so my first thought is factoring by grouping. And I think that would be a good way to go on this one. Remember, to factor by grouping, we're going to pair them up. We're going to shuffle the negative into the second pair. And then we're going to factor out the greatest common factor in each pair. For the first pair, they both have at least 2 x's. We can factor out an x squared. We'll have an x minus 4 left over. 9 and 36 are both divisible by 9, and I'm going to use -9 so that when I divide both of these things by -9, I get x minus 4 left over. Remember, for factoring by grouping to work, the leftover parts here in parentheses must match. And they do, so we're going to factor that out. Okay, and we can actually do one more factoring step. The x minus 4 is done. We can't really break that down any further, but the x squared minus 9, this is a difference of squares. And when we solve by factoring, once we've factored it, then we set each part equal to 0. I think probably we can do that part in our head at this point, right? So if I set x minus 4 equal to 0, I'm going to get 4. If I set x plus 3 equal to 0, I'm going to get -3. And if I set x minus 3 equal to 0, I'm going to get 3. Okay, and these are my zeros. If you wanted to write them as points, it would be 4, 0, -3, 0, and 3, 0. These would be my x-intercepts. Okay, so if we were going to make the graph for this function, we could start by plotting these 3 points right on the x-axis. If we go all the way back to the top here, notice the degree is 3. So we could have found at most 3 zeros, and we did find all 3 of them. Okay, so these two examples kind of give you a good idea of the two methods that are usually used to solve for the zeros. You can do factoring, which is what we've done here, or you can do this root method. One of the books I used to use called this the extraction of roots. Okay, so those are the two main methods that we can use to find the zeros. All right, after we find the zeros, the next step is to talk about the end behavior. So the end behavior, like you could probably guess, describes the ends of the graph. So these squiggles, their ends go to either positive infinity or negative infinity. And there are two ends. So two ends, two choices, either going up or going down, okay? So we're going to look at all the different possibilities and show you what it's determined by. So the end behavior is determined by what's called the dominating term. And the dominating term is the term of the polynomial with the highest degree. So if we're writing it from largest exponent down to smallest, this is going to be the term in the very front. Okay, and sometimes we write out the terms kind of in this general way with a's and n's and lots of different variables. Really all you need to know is it's the term at the very front of the polynomial that we're using. Okay, so we use that term in the front to decide what the ends are going to look like. So ax to the n is the term in the front. And so we're going to look at two things. We're going to look at the exponent. We want to know, is the exponent even or is it odd? If the exponent is even, then the ends are going to travel together, kind of like a parabola, both ends going in the same direction. If the exponent is odd, then the ends are going to travel in opposite directions, kind of like x cubed, where one end goes up and one end goes down. Okay, and then we look at the number in front, the value for a. We want to decide, is it positive or negative? So this would decide whether it's been reflected or not, right? That's sort of how that ties into what we've already looked at. So I usually use the value for a to decide what happens on the right-hand side. And these kind of work together, the a and the n. So if the a is positive, that means that the right-hand side is going to go up. As x gets really big, the y value is going to get really big in a positive way. And so it's going to go up towards infinity. If the exponent is also even, then they're going to travel together and they're going to both go up. Okay, if a is positive, but the exponent is odd, then the right-hand side is going to go up, but they're going to travel in opposite directions, so the left-hand side is going to go down. If the value for a is negative, then basically what we just said is going to be reflected over the x-axis. So I use this to determine the right-hand side. So if a is negative, that means that the right-hand side is going to go down. If the exponent is even, then they're going to travel together, so they're both going down. If the value for a is negative and the exponent is odd, then again the right-hand side will go down, but because the exponent is odd, the ends are going to travel in opposite directions, and the left-hand side is going to go up. Okay, so let's try that out. We'll just do the same two functions we were just practicing with. So for this first one, we have f of x is 2x to the fourth minus 162. Can you spot the dominating term? It's this term in the front with the highest degree. So if we look at this and compare it with this chart we have right here, the exponent is even, which means that the ends are going to travel together. We're looking at. And the number out front is positive, which means It's sort of opening up, although it's not necessarily a parabola, right? And I put these dot, dot, dot in the middle because remember these are squiggles, so some crazy interesting highs and lows may happen in the middle, but we're just talking right now about the ends. So the ends for this one will both travel up. And you are welcome to draw a little diagram to represent that. It's a lot easier than trying to put it into words, okay? So when I ask you for the end behavior, you can just draw this little diagram. That's totally fine. Okay, what about this second one? You can see that the dominating term here is an x cubed. And I know that there's no number written in front here, but it's an implied 1 in the front for the value of a. So the exponent here is odd, and the number out front is positive. So we have this scenario. That means that the right-hand side is going up because I have a positive number in the front, but my exponent is odd, so the left-hand side is going down. All right, so let's try and put those together a little bit. Here's an example. So this one actually has already been factored for us. In a lot of the other examples, we'll have to do our own factoring. Okay, so what are the zeros of the function? We're going to make f of x 0. And then we're going to set each part equal to 0. And I think we can do that part in our head. So there are the zeros. What is the end behavior of this graph? The dominating term would be the term of highest degree if we multiplied this all out. So I don't want to do all of the multiplying, but let's just pretend we multiplied this all out. X times x times x would have x cubed in the front plus a bunch of other stuff. Right? That's our dominating term. So that means that the right-hand side is going to go up and the left-hand side is going to go down. The way we're going to integrate all of this information together is we're going to make a rough sketch of what the graph would look like. And we're going to start with the zeros. So we have a 0 at -2, at +1, and at +4. Then we can put the end behavior. The end behavior starts at the outermost zeros. Okay, for the next part we haven't talked about yet, but this graph is going to cross over the x-axis, and we're estimating its shape. All right, so we'll delve into that more in the next video. Thanks for watching.